Today, I want to follow up on my talk on Newton's universal gravitation law and give some of the details of how binary mechanics might handle that situation that's left open if we discount mass as an important variable. Okay, road to the law of motion. In 1994, in the binary mechanics paper presented full quantization of energy, space, and time, with equations for system state and its time development, without use of any unexplained measurements wrongly known as fundamental constants. As you know, these unexplained measurements are input values in the standard model presented by particle physicists. Binary Mechanics was published in the Journal of Binary Mechanics, which is online, in 2010. In 2011, this is on our road to the law of motion, the proton and electron bit cycles were discovered using binary mechanics simulation software. If a simulation initial condition had only one quanta defined as a one state, after repeated application of the time development laws, the quanta was observed to return to its initial position. Thus, particle spin appeared to be a physical reality. If a simulated volume is cooled to 0 Kelvin, well, how can we do that? Well, the nice thing about having a simulation is that all of the one-state quanta that leave the simulated volume, they're exiting the top, the bottom, the front, the rear, the right, the left, they exit. They're gone. And eventually, you'll find no more quanta are leaving. You're at 0 Kelvin. All radiation and or kinetic energy, because some of those quanta leaving could actually be particles with kinetic energy, right? So if you cool the simulated volume down to 0 Kelvin by just simply letting this run and let the quanta that leave the volume be lost forever, this cyclical quanta motion continues. For those quanta that remain, they're still circling in these bit cycles that I described. Quanta remain captured. This is an important word to create an image of what's going on. In their bit cycles, they're captured, and particle motion was found to be zero. Why? Because for a particle to move, a quanta must leave one bit cycle and go to the next. That is, no quanta exit a bit cycle and enter another when there's zero particle motion. This result revealed the mechanism of particle motion, namely quantum motion between bit cycles. So the road to the law of motion, which is key to unlocking this puzzle, is based upon an understanding of what the mechanism of particle motion is. And as far as I know, this is fairly unique in binary mechanics. Certainly Newtonian mechanics and the standard model and any other theory that I know of doesn't really address the question of how things move. They just describe that they do move, and they move so many meters and or with such a velocity or acceleration, but not the mechanism of motion. Meanwhile, proprietary binary mechanic technology called the bit function analysis showed that each of the 8 binary mechanic elementary particles are composed of 3 quanta. This is an important point. Thus, for a particle to appear at its location called a spot, 1 to 3 quanta would have to enter that location. Higher density spots with 2 quanta are more likely to form particles since only 1 more quanta is required. Here we're getting very close now to the logic of how we arrive at, from the mechanism of particle motion, how we arrive at the law of motion. The law of motion is based on understanding of the mechanism of motion. The law of motion is that objects tend to move toward higher energy density. So here's a displacement of an object of diameter d, higher energy density on one side and lower on the other side. So let's let the energy density gradient equal the difference between the two densities, 1 and 2, divided by the distance, the object diameter. With displacement dx of 1 quanta in an area A, motion law force is going to be the displacement, which is in meters, an area, which is in meters squared, and this density gradient. What we did in binary mechanics is take the complex amplitude, which is squared to get a probability only in conventional, what I call antiquated, old-fashioned, obsolete quantum mechanics. And we took the absolute value of x and the absolute value of y and limited their values only to 0 or 1, that quantized energy. And this thing is called the spot unit. Now, when we take 3 spot units, which are 2 volumes of size L cubed together, 1 and 2, and there's 2 kinds of quanta, the M quanta and the L quanta, and combine 3 of them in the X, Y, and Z dimensions, we get a spot, which is a part of the structured space model of binary mechanics. Now you see the bit cycle for the electron right here. If one of these is in the 1 state, it's going to circle, if it's not disturbed, forever in a cycle. The gray dot in the middle here is the axis. And so we have like a spinning top. And so this provides an actual physical model of what your antiquated, non-updated quantum mechanics or conventional quantum mechanics say is just something that we imagine, that when they talk about the 1/2 spin of the electron, they just say, well, we're just imagining that. It really doesn't happen in real life or in physical form. Binary mechanics asserts, yes, it does happen. Now, we then can use this idea of the spot. Turns out there are 8 permutations. The direction of the L bit, it could be going one way or the other. The sign of the M bit could be plus or minus as far as electric charge and color goes. And to make a long story short, we define the spot cube as a spatial model. The purpose of today's talk is not to really go into detail about this particular subject of how we created this image of the spot cube. Equation 5 will give you the sign of the M bits, and equation 6, the direction of the L bits, and all of this put together with different permutations give you the image of what we just talked about. The purpose of showing this slide is just to show you that there is the math behind this formulation of the system state. And that's required in order to write a simulation computer program. You have to have this math. The scalar and the vector bit operations, number 2 and 3 here, don't apply to what we're going to talk about today. That has to do with electromagnetics. Of course, the electric is the scalar, and the magnetic or the vector, A is your vector bit operation, which brings in magnetism. But since we're only dealing with 1 bit circling, these operations don't apply. What gives you the bit cycles is 1 and 4, the strong bit operation and the unconditional bit operation. In the unconditional bit operation, we're just shifting the bits in the direction of the L locus arrows. So here is our home version of binary mechanics bit cycles, showing you the bit cycle for the electron. Okay, now here's more the pro version of the bit cycle. Now at time equals 0, if we have a 1 state shown by the black color of the symbol, the arrow indicates the L bit, it's going to shift at time equals 1. In the strong bit operation, it's going to transfer from the X dimension this way to the Y dimension, up and down, over to here, as we see at time equals 1. That's the strong bit operation. Now, what more is there to say about it? What if both of the loci are in the 1 state, or as we say in ordinary English, contain quanta, at time equals 0. The M and the L bit both in the 1 state. What happens is that the strong bit operation is blocked, okay? If it's blocked at time equals 1, nothing has happened. There has been no transfer. So above we see a transfer when the other bit in the cycle is empty or in the 0 state, but if the other bit in the source spot unit is in the 1 state, there is no transfer. This is the pro version of the strong bit operation and bit cycle. So what can happen? Let's go back to the home version. So we see that this bit right here was focused in the previous illustration. There are two alternatives. One is that it transfers to the Y spot unit in the Y direction here, as we showed just a moment ago, or it is not transferred. It is blocked because both of these bits are in the one state. In that case, in the next subsequent time tick, that one state quanta here will move forward and move from one spot to another. And so that's how we exit from the spot. So we have two alternatives. The strong bit operation creates our cycles. And if there is what I call inertia, it's the product of the L bit and the M bit. If the product is 1, it means that we have inertia and that the strong bit operation is blocked. So therefore, this bit in the next unconditional bit operation will shift. I gave you the simple version of the electron bit cycle, which has 6 locations. That's a rather simple situation. Here is the proton bit cycle. You might remember in my image of the spot cube in the particular angle it was displayed in the schematic illustration, we had the red quark, matter quark up here in the upper left, and off to the right was the blue, dark blue, and down at the bottom was the dark green. These are your matter quarks. The lighter green and lighter blue and lighter red would be your antimatter quarks. Notice at the top here, there are actually 4 bit loci, which are actually outside of the original spot cube, but are part of the proton bit cycle. Off to the lower left, there's another one. And off to the lower right is another 4 bits, which are outside the what we might call the home spot cube for that proton bit cycle. Now, there's 42 different locations here, which could either be in the 1 state or the 0 state. So you're looking at all of the possible complexities of the whole family of hadron particles, including the proton. The proton and electron bit cycles define the physical basis for the concept of particle spin, indicating that angular momentum is an intrinsic property of the spot and spot cube model of structured space. The fabled sea of virtual particles may now be understood as cycles containing fewer quanta than demonstrated thresholds required for observed particles. The proton bit cycle exhibits known hadron properties: the non-spherical proton shape, which I just emphasized, 2, color confinement, and number 3, the 2 to the 42 possible states based upon the 42 quanta loci in the cycle. The proton and electron cycles share the same spin axis, the solid diagonal of the spot cube between the electron and positron spots. The proton and electron quanta cycles exhibit opposite spin directions. I didn't notice this until I prepared this talk, the home version of the proton bit cycle, and noticing, oh my gosh, its spin direction is opposite to the spin direction of the electron bit cycle. This must have major importance, but that's a discovery I made just by preparing this talk. If a 1-state quanta can leave the electron bit cycle, it must transverse 4 length distances, 1, 2, 3, 4, to get to a corresponding position in the next electron bit cycle. So this would be quark-mediated electron motion. Okay, so basically, I'm showing here schematically the same thing from a different point of view. If at time 0, let's just look at the middle columns. The odds of a quanta in the middle row here of going up or down. If it goes down, there's a greater odds of forming a particle at time equals 1 compared to if it goes up. And so gravity is actually a quanta density gradient. That's what this slide is saying. It's just another way to look at the law of motion. Thank you for your attention.